We continue with our investigation of traditional machine learning approaches to graph level predictions, and now we are going to focus on link prediction tasks and features that capture structure of links in a given network. So the link level prediction tasks is the following. The task is to predict new links based on the existing links in the network. So this means at test time, we have to evaluate all node pairs that are not yet linked, rank them, and then proclaim that the top k node pairs, as predicted by our algorithm, are the links that are going to occur in the network. And the key here is to design features for a pair of nodes. And of course, what we can do, as we have seen in the node level tasks, we could go and let's say concatenate the features of node number 1, features of the node number 2, and train a model on that type of representation. However, that would be very unsatisfactory because this would lose much of important information about the relationship between the two nodes in the network. So the way we will think of this link prediction task is two-way. We can formulate it in two different ways. One way we can formulate it is simply to say links in the network are, let's say, missing at random. So we are given a network, we are going to remove at random some number of links and then trying to predict back those links using our machine learning algorithm. That's one type of a formulation. And then the other type of a formulation is that we are going to predict links over time. This means that if we have a network that naturally evolves over time, for example, a citation network, a social network, or a collaboration network, then we can say, we are going to look at a graph between time 0 and time 0 prime, and based on the edges and the structure up to this time t0 prime, we are going then to output a ranked list L of links that we predict are going to occur in the future. Let's say that are going to appear between times t1 and t1 prime. And the way we can then evaluate this type of approach is to say, we know that in the future n new links will appear. Let's rank the potential edges outputted by our algorithm, and let's compare it to the edges that actually really appeared in the future. This type of formulation is useful or natural for networks that evolve over time, like transaction networks, like social networks, where edges keep adding. While, for example, the links missing at random type formulation is more useful, for example, for static networks, like protein-protein interaction networks, where we can assume, even though this assumption is actually heavily violated, that, biologists are testing kind of at random connections between proteins, and we'd like to infer what other connections in the future are going for biologists are going to discover in the future, or which links should they probe with their wet lab experiments. Of course, in reality, biologists are not exploring the physical protein-protein interaction network at random. They are heavily influenced by positive results of one another. So essentially, some parts of these networks are really well explored, while others are very much underexplored. So with these two formulations, let's now start thinking about how are we going to provide a feature descriptor for a given pair of nodes. So the idea is that for a pair of nodes xy, we are going to compute some score C xy. For example, a score could be the number of common neighbors between nodes x and y. And then we are going to sort all pairs xy according to the decreasing score C, and we will predict top m pairs as the new links that are going to appear in the network. And then we can, at the test time, we can actually go and observe which links actually appear and compare these two lists, and this way determine how well our approach, our algorithm is working. We are going to review 3 different ways how to featureize or create a descriptor of the relationship between two nodes in the network. We are going to talk about distance-based features, local neighborhood overlap features, as well as global neighborhood overlap features. And the goal is that for a given pair of nodes, we are going to describe the relationship between the two nodes, so that from this relationship you can then predict or learn whether there exists a link between them or not. So first, we talk about distance-based feature. This is very natural. We can think about the shortest path distance between the two nodes and characterize it this way. So for example, if we have nodes B and H, then the shortest path length between them equals 2. So the value of this feature would be equal to 2. However, if you look at this, what this metric does not capture. It captures the distance, but it doesn't kind of capture the degree of neighborhood overlap or the strength of connection. Because, for example, you can look in this network, nodes B and H actually have two friends in common. So the connection here, in some sense, is stronger between them than, for example, the connection between node D and node F. Because they only have there is only one path, while here there are two different paths. So the way we can try to capture the strength of connection between two nodes would be to ask, okay, how many neighbors do you have in common, right? What is the number of common friends between a pair of nodes? And this is captured by the notion of local neighborhood overlap, which captures the number of neighboring nodes shared between two nodes, V1 and V2. One way to capture this is to simply say what is the number of common neighbors, right? We take the neighbors of node V1, take the neighbors of node V2, and take the intersection of these two sets. A normalized version of this same idea is Jacquard coefficient, where we take the size of the intersection divided by the size of the union. The issue with common neighbors is that, of course, nodes that have higher degree are more likely to have neighbors with others. While here in the Jacquard coefficient, in some sense, we are trying to normalize by the degree, to some degree, by saying what is the union of the number of neighbors of the two nodes. And then the other type of local neighborhood overlap metric that actually works quite well in practice is called Adamich-Adar index. And simply what this is saying is, let's go over let's sum over the neighbors that nodes V1 and V2 have in common, and let's take 1 over the log their degree. So basically the idea here is that we count how many neighbors two nodes have in common, but the importance of a given neighbor is low, decreases with its degree. So if you have a lot of neighbors in common that have low degree, that is better than if you have a lot of highly connected celebrities as a set of common neighbors. So this is a feature that works really well in social network. Of course, the problem with local network neighborhood overlap is the limitation is that this metric always returns 0 if two nodes do not have any neighbors in common. So for example, in this case, if we would want to say what is the neighborhood overlap between nodes A and E, because they have no neighbors in common, they are more than 2 hops away from each other, then if in such cases the value of that it will be returned will always be 0. However, in reality, these two nodes may still potentially be connected in the future. So to fix this problem, we then define global neighborhood overlap metrics that resolve this limitation by only focusing on 2-hop distances and 2-hop paths between a pair of nodes, and consider all other distances or the entire graph as well. So let's now look at global neighborhood overlap type metrics. And the metric we are going to talk about is called Katz's index. And it counts the number of all paths of all different lengths between a given pair of nodes. So now we need to figure out 2 things here. First is, how do we compute number of paths of a given length between 2 nodes? And this can actually be very elegantly computed by using powers of the graph adjacency matrix. So let me give you a quick illustration or a quick proof why this is true. So first I want to give you the intuition around the powers of adjacency matrix, right? The point is that what we are going to show is that computing number of paths between 2 nodes reduces down to computing powers of the graph adjacency matrix, or essentially taking the graph adjacency matrix and multiplying it with itself. So first, graph adjacency matrix, recall it has a value 1 at every entry uv if nodes u and v are connected. Then let's say that p uv superscript capital K counts the number of paths of length k between nodes u and v. And our goal is to show that if we are interested in the number of paths of length k, then we have to compute a to the power of k, and that entry uv will tell us the number of paths. The capital K here is the same as small k. So the kth power of a measures the number of paths of a given length. And if you think about it, right, how many paths of length 1 are there between a pair of nodes? That is exactly captured by the graph adjacency matrix, right? If a pair of nodes is connected, then there is a value 1, and if a pair of nodes is not connected, then there is the value 0. Now that we know how to compute the number of paths of length 1 between a pair of nodes, now we can ask how do we compute the number of paths of length 2 between a pair of nodes u. And we are going to do this via the two-step procedure. And we are going to do this by decompose the path of length 2 into a path of length 1 plus another path of length 1. So the idea is that we compute the number of paths of length 1 between each of u's neighbors and v, and then add 1 to that. So the idea is the following. The number of paths between nodes u and v of length 1 of length 2 is simply a summation over nodes I that are the neighbors of the starting node u times the number of paths now from this neighbor I to the target node v. And this will now give us the number of paths of length 2 between u and v. And now what you can see, you can substitute here back the adjacency matrix. So all this is a sum over I, ui times aiv. So and if you see this is simply the product of matrices of adjacency matrix A with itself. So this is now the entry uv of the adjacency matrix A squared. And now by induction we can keep repeating this and get higher powers that count paths of longer lengths as this is increasing. Another way to look at this, here is a visual proof, is that what is A squared? A squared is A multiplied by itself. So when we are interested in a given, let's say, entry, here these are neighbors of node 1. These are now the number of paths of length 1 between one's neighbors and node number 2. So after the multiplication, the value here will be 1, which will mean that there is one path of length 2 between node 1 and node 2. So this is how powers of adjacency matrix give count paths of length k between a pair of nodes in the network. What this means is that now we can define we have developed the first component that will allow us to compute the CATS index, because it allows us to count the number of paths between a pair of nodes for a given k. But what we still need to decide is how do we do this for all path lengths from 1 to infinity. So to compute the paths, as we said, we are going to use powers of the adjacency matrix. The adjacency matrix itself tells us powers of length 1. Square of it tells us paths of length 2. And the adjacency matrix raised to the power L counts the number of paths of length L between a pair of nodes. Now the CATS index goes over path lengths from 1 all the way to infinity. So the CATS index global neighborhood overlap between nodes v1 and v2 is simply a summation of L from 1 to infinity. We have this beta raised to the power of L by basically a discount factor that gives lower importance to paths of longer lengths, and A to the L counts the number of paths of length L between nodes v1 and v2. And now what is interesting about Katz's index is that we can actually compute this particular expression in a closed form. And here is the formula for the Katz's index again. And basically here is a closed form expression that will exactly compute this sum. And the reason why this is true, or why there is an equality, is this: we notice that this is simply a geometric series for matrices, and for that there exists a closed form expression that all that it requires us is take the identity matrix minus beta times adjacency matrix, invert that, and then subtract the identity matrix again. And the entries of this matrix S will give us the Katz's neighborhood overlap scores for any pair of nodes. So to summarize, link level features, we described three types of them. We talked about distance-based features that uses, for example, shortest path between a pair of nodes and does not capture neighborhood overlaps. Then we talked about this neighborhood overlap metrics like common neighbors, Jacquard, and Adami-Chadar that captures in a fine-grained way how many neighbors does a pair of nodes have in common. But the problem with this is that nodes that are more than 2 hops apart, nodes that have no neighbors in common, the metric will return value 0. So the global neighborhood overlap type metrics, for example like Katz's, uses global graph structure to give us a score for a pair of nodes, and Katz's index counts the number of paths of all lengths between a pair of nodes, where these paths are discounted exponentially with their length.